Assalamu alaikum everyone. Hello, welcome. My name is Abdulrahman Alabyad. I'm a second year medical student. And today we'll be discussing the lecture, the physiology, the tubular functions 1 and 2. I don't know what you guys heard about this lecture before, but what everyone probably says from your seniors is that it is the hardest lecture that you might face in renal. However, just keep in mind, renal physiology is going to be, inshallah, really easy, but out of all the easy lectures, this is probably be the toughest one. The reason is because of the many receptors, but inshallah throughout the lecture I'm gonna explain, give you guys a way that you could use so that the receptors would be easy as you're going through them, and inshallah overall the lecture will be easy. And I will send you my slides after I'm done. I might edit it a little bit, add a little more questions, because I couldn't find any before the lecture. I only had 3, so I might edit it and add a little more questions. And okay, so if you have any questions, just you can type in chat or you can unmute your mic and let me know. If I was going a little too fast as well, please let me know. Inshallah, I'll try to slow down. All right, with that being said, we can begin. So now to start, first thing I need to understand, I need you guys to understand that before we get into the lecture, let's go over some basic general anatomy or some general information that were mentioned in the slides, and some information that I want to just put it straight out before we begin, so that it will help simplify everything else that we're going to be discussing. Now, the first part, this one was this picture is in your lecture. However, it is just for basic understanding. It's not something that you might actually get questions about. So, but I mean, probably 90% of you already are familiar with all this terminology. However, if you're not, I'm gonna explain them real quick right now. And from this point on, they're going to be your basis. These stuff this terminology, whenever you read them, just remember them, and you should have them on the back of your mind at all. You don't need any more introductions about them. So these are basically discussing different pathways, how substances can move through the cells, okay? So the first one is diffusion. Diffusion is basically when we get small substances such as gas particles, they just move from space to the cell or out of the cell simply by just them moving through the membrane, okay? Such as lipophilic substances. I'm gonna mention it just so that you guys can remember it whenever diffusion is associated with that, okay? Lipophilic substances can also pass through diffusion. Lipophilic because they love fats, and as you know, the membrane of the cell is made of fats, so that's why they can diffuse. Tamam? Ion channels, they're basically some receptors that allow ions to move in or out of the cell. There are other receptors such as, or referred to as facilitated diffusion. They could be primary active or they could be secondary active, or you can have just a facilitated diffusion where there is a receptor that allows a substance, for example, such as glucose, or as you learned in mol GLUT1. So it's a receptor that facilitates the movement of glucose because it can't move through diffusion, okay? So it's facilitated diffusion. This is referred to as passive transport. These 3 methods are passive transport. And then you get the active transport. Active could be 2 types. Why is it called active? It's because it's using ATP. So you get primary active, you got secondary active. Primary active is basically when you are taking a substance against its concentration gradient. Or if it was 2 substances, then both of them are against their concentration gradients. In that case, and the most common primary active transporter is the sodium potassium ATPase. And it's found in, I think, I'm pretty sure in every cell. And it's the most important receptor. So this is a primary active, okay? Both are against, and it's using ATP. Secondary active, then you have one that is against and one that is going with its concentration gradient. And with that happening, so what happens is that the one that is going with the concentration gradient is going to be providing the energy for the other one to go against its concentration gradient, because anything that wants to go against requires energy. The next one is paracellular. Paracellular, it's like para, you know how something is parallel, so it's parallel to each other. So paracellular is between the cells. Intercellular, it's just between the cells as well. And then you got transcellular. Transcellular is basically through the cell. Okay, so all these methods are examples of transcellular. Tamam? Yeah, this is not something that you're gonna get questioned on, but this is your basis from now on. Whenever you hear this stuff, you don't need anyone to explain them to you. Just memorize them in the back of your head, understanding stuff. This is another lecture or another picture, which has basically the same idea of the previous slide. Just remember this stuff and you don't need anyone else to explain them to you again. So now we're going to talk about the driving forces. So there are 2 main driving forces. You got a concentration gradient and an electrical gradient. What do we mean by an electrical gradient? We have cations, anions, a positive charge and a negative charge. So this is the electrical, okay? So positive and a negative charge, they have charges. So they are basically, we kind of consider them that they have electrical energy or something like that. And not just electrics, electrics, it's charges, tamam? So As you can see here, there is a high negative charge, and this here has or no charge. Usually what happens is that if there is a negative charge, it's going to attract the positive, because opposite charges attract and similar charges repel. So if there is a so for example, saying this part here is negative, right? So if there is any sodium ions in here, then we're going to attract them into this. Okay, let's look. Okay, ignore this one. If there is any positive ions here, that we have only an ion channel, because this is an ATPase. I'm going to talk about it in a second. If you have only an ion channel, a simple channel that moves the ions through their concentration gradient, okay? So we have sodium here, which is positively charged. Let me open up a pen. Okay, so if we have a positive charge here, and there is an ion receptor, then the positive charge will go into the cell because we have negative. And if there is a negative charge here, and there is a receptor, the negative charge will actually move from outside or from inside to outside, okay? Just electrical gradient. And this is an ATPase. What the ATPase does, as we just explained in the previous slide, since it's using ATPs, so both of them are against their concentration gradient. And just a general idea, you don't need to know it for this lecture. So no, sodium is more outside the cell and potassium is more inside the cell. Later on, you're gonna have to know it, but this is a basic concept. For next year, you're gonna have to keep that concept in the back of your head. But I'm gonna say it in general now. Potassium is higher inside the cell, while sodium is usually higher outside the cell. So when we're moving sodium from inside the cell outside, then this is going to need ATP, because at the same time, potassium is moving against its concentration gradient. Potassium is always inside the cell, sodium is outside the cell mostly. Tamam? Now, okay, see, yeah, this is here, right? It says the electrical gradient, the potassium is leaking, because it's positive charge, and here there's a negative. Tamam? Now, concentration gradient, what does this mean? It means that a substance moves down its concentration gradient. Tamam? So, for example, here we have a high concentration of sodium, while here there is a low concentration of sodium. So what happens is that this sodium is going to move inside the cell. Now, theoretically, usually, like the ion wouldn't want to move to stay inside the cell. It's usually comparing between like a space that you have in your body, such as in our lecture, the lumens or the tubular fluids, and the blood. Tamam? So they're trying to compare actually the electrical gradient that's being compared, like the actual gradient here compared is the -3 and the 0, and the 145 and the 145. So once they are equal, there's no more concentration gradient, then the sodium is no longer going to move. Tamam? So I apologize, I did explain it here on the -70, but actually what I should have explained it is according to the 0. Tamam? So the comparison is between inside the cell and, I mean, not inside the cell, between like one space and the other space. So the blood vessels and the tubular fluid. Tamam? Okay, so this is just introduction that you need to know. Now, this part here, I added in order to basically introduce you to the lecture so that you can have an idea about what we are going to be discussing. Tamam? So now, anatomy to physiology, I'm trying to relate what happens. So we already took the glomerulus lecture. Tamam? So what happens here? You got the afferent arterioles, then you got the capillaries, and then you got the efferent arterioles. In the glomerulus, all it does, it takes in everything that comes, it filters it, and I think, like, I'm pretty sure it was that it filters everything except proteins, because proteins are big. If the glomerulus was filtering proteins, then we have a disease in the glomerulus, tamam? Or like nephrotic syndrome. So glomerulus takes in everything, ions, glucose, water, anything, and just filters it. It doesn't pick whatever it wants, tamam? And then they go through the tubular fluid. Now, the tubular system is made of these structures. Let me just move this. Okay, so we got the proximal tubule. The proximal tubule is the one closest to the glomerulus. Proximal means closer, so we're comparing it to the glomerulus. And then you got the loop of Henle. There's the descending limb, and then there's ascending limb, which has a thin part and a thick part. And then you got the distal tubule and the collecting duct, and that's it, okay? So the glomerulus, what it does, why do I have the glomerulus here in purple and the proximal tubule in bolded? Because the glomerulus, all it does, as we said, it takes in everything and it filters it straight into the tubule system, okay? Now, at this point, like, we don't want to filter out everything in our body. There are certain stuff that, for example, glucose, which is our energy, right? We need to take this, we need to keep it in the body. However, the glomerulus doesn't do that. So the main function of the entire tubular system, but not only the proximal, the entire system is basically regulating what are the stuff that we need in our body that we don't want to get rid of, because, you know, at the end of this, like at the end of this pathway, they will get secreted in your urine, so you no longer have these stuff. So what we're doing is that we're focusing on what are the stuff that the body needs that we are going to have to take back from this tubular system and put it back in the blood. And at the same time, the tubule system can also see what is excess in the body that the glomerulus doesn't filter, and then they put it in the tubules. So we're trying to, in the tubular system, we're trying to regulate our body needs. We're trying to get rid of the stuff that we have in excess that the glomerulus couldn't get rid of, and we're trying to restore the important stuff that the glomerulus removed. So again, this is basically just discussing everything. As you can see here, we got the glomerulus. It takes out everything. It takes out water, takes out sodium chloride, sodium ions, chloride ions, potassium, bicarbonate, glucose, amino acids, and you can't just get rid of all the stuff, because if we get rid of it all, and then like imagine you're just urinating every day all the water in your body, and you're not restoring it. So immediately you're gonna get in hypertension situation and you're gonna die. So we need to reabsorb the water and other stuff. Proximate tubule is the main worker. What exactly do we mean by the proximal tubule is the main worker? As you can see here, that the proximal tubule, I mean, you can't really notice it in this picture, but once we get into the actual physiology, you're gonna, forget, don't look at the picture, just understand it with me. So I said we filter water, sodium chloride, potassium, bicarbonate, glucose, amino acids. They're no longer in your blood, okay? Now they are in your urinary system. So your body thinks that you don't have these stuff, tamam? Let's begin with some basic stuff such as water or glucose or amino acids. If you are getting rid of this stuff and putting them in your tubular fluid, do you want them to pass through the entire tubular system, like all the way to the collecting duct? Until then, you'd be like, oh, okay, let me just bring this back to my body. Or if it's something important, when you have something urgent on your to-do list, then this would be like the first thing you're going to do. So if we said that, for example, that we're going to discuss later, but just keep in mind now, glucose and amino acids, they are very important because we need them to make proteins. We need them to make, or like glucose is for our energy. So immediately after the glomerulus filters them, the first thing that we're trying to do, or the closest structure, is going to be, oh, there it is. Okay, nutrients. So the first thing that we're trying to do is that we're trying to take these important stuff that we just filtered, we're bringing them immediately back to the body, because they don't have to go through this entire pathway till we be like, oh, okay, we need them. So because we need them, the proximal tubule is the main worker, because he's going to be collecting as much as much stuff that we need and reabsorbing them back to the body. Okay, so I got a question. So we reabsorb them, right? Yes, exactly, because we need these stuff, so we don't want them to stay there. So okay, with that being said, this is my most general introduction, and this will make, inshallah, everything else easier, except for a little bit in the physiology part. So glomerulus filters everything. The tubular system is trying to get, the glomerulus filters everything. It doesn't really like pick or choose. Anything that can pass the glomerulus gets filtered. In the tubular fluids, in the tubular system, we basically try to regulate between the inside and the outside. If we have an excess in the outside, we're trying to put it in the tubular fluid as well, that because an excess, the glomerulus couldn't fill all this excess because there is a capacity. And if we have too little, then we take it back into the body. If there is something that is very important and we don't really want to like have it, or we don't really want to stay for a long time without it, we're going to be taking it back or reabsorbing it into the blood as soon as possible. And so what is the closest place that we can do this stuff? It is going to be the proximal tubule. So the proximal tubule is reabsorbing the most. Okay, I'm saying it right now. The proximal tubule reabsorbs the most stuff. So then some other points that I just mentioned them here, but you're going to focus on them later in the descending limb is going to be filtering water only. We're going to discuss it later in a second, but just keep in mind, descending limb reabsorbs. Okay, so reabsorbs water only. Okay, so in case this for some of you, let me just, like, because of the arrows, I'm gonna just mention. So this is like what's inside the blue. This is the tubular system. So if we say, for example, that the water is going from the blue to outside, this part here, the cortex, the medulla, these are basically like, if you remember from the histology, the cortex, the outer inner medulla, these are basically the kidney. So if we're taking it from the tubular system to the actual like interstitium of the kidney, or like, so the interstitium is basically the connective tissue of the kidney. So we're basically taking it back to the kidney so that it can go back to the blood. Okay, so anything that is going outside of the blue, then it's not going to be urinated, because here, right here, the blue is going to end in the ureter, through the bladders, and then outside the body. Okay, so for example, this part, the ascending limb, it is going to be reabsorbing back into the body only the sodium chloride. There's no water that's going to pass. And then you got distal tubule, and then you got collecting duct. Two are going to be the final parts. So if we have already, as we said, like according to our story, there's something that's very important. We reabsorbed it immediately to the body. So anything that's towards the end, then all what's there in the ends, like the small minor stuff that we could or couldn't, depends. You can change the variable around. So around here, this is why the distal tubule and the collecting duct, they're towards the end. So they're basically modifying, like trying to fine tune. And as a result of that, like how can they know, for example, that if, let's say, there is a lot of sodium in the body, so how are the collecting duct and the distal tubule going to know that, oh, okay, there's a lot of sodium, so let me remove the sodium from the body? This is done through an action of hormones, okay? And we'll discuss them in a second later. So this is a basic introduction, and this one will make everything from now on much easier. So do you guys have any questions before we get into the actual lecture? Is it all clear? Okay. Let's go. So now, the glomerulus just filtered out everything, right? And now we're in the proximal tubule. The proximal tubule is the main worker guy. I'm gonna say it right now in the proximal tubule. However, this concept that we're gonna discuss in a second, it is for all the duct system, and in some sense for like almost every cell in your body. Tamam? The sodium potassium ATPase pump. This is the most important protein pump, or the most important protein channel, whatever you want to call it, inside the body. What it does, sodium potassium ATPase takes 3 sodium outside the cell and 2 potassium inside the cell. As a result of that, we're gonna have as you learn like MSK, there is an resting membrane potential. It is because of the sodium potassium pump. Because of the sodium potassium pump, we're creating a concentration gradient, because we said there is more potassium inside the cell and more sodium outside the cell. So we're making even a bigger concentration gradient. And because of this sodium concentrate, like mainly sodium, okay? So because of this sodium concentration gradient, because it's much higher now outside the cell, so much higher outside the cell and much lower inside the cell, the sodium. So as a result of that, we're gonna have a bigger concentration gradient. And as you remember, we said the concentration gradient will cause the sodium to move from an area of high concentration to area of low concentration. So if we said here there was high concentration of sodium right now, then it will probably start going into the cell, to like from area of high to low concentration. Okay. Now, so why exactly is it sodium? Because the importance of a sodium gradient, or having like a concentration difference in sodium, is that the sodium gradient is, or the sodium itself is associated with many receptors or co-transporters. Basically, sodium is needed to push a lot of other stuff into the cell. Okay, I will discuss this stuff now. Tamam? So the most important thing is that the sodium potassium ATPase is allowing everything to happen, because it's creating the main concentration gradient, which is the sodium. And this sodium concentration gradient is what we are going to use to allow our transport of the multiple other stuff that we need. So let's begin with the proximal tubule. I know it's a lot, but let's go through it step by step. It's very easy. Tamam? So sodium potassium ATPase, we always begin with that. This is our step 1. Okay? It created the concentration gradient of sodium. Now inside the cell, we have low sodium because the sodium is outside the cell, right? So it's because the sodium is right now outside the cell. And outside the cell here, now we have high sodium. Tamam? So where would the sodium want to go? The sodium now wants to move from here into here. Okay? Ignore this channel for a second. Just focus. The sodium wants to go from here to here. Okay? So now we said that the glomerulus is going to filter out everything. Some of these stuff are very important to us and we need them, such as the glucose, which is used for our energy, amino acids, which we're using for protein synthesis, lactates, phosphates, which are all mentioned here. So like, you don't really need to know all of them by step, but I think it's really important to know lactate and phosphate. Okay. Look, I don't want to tell you, yeah, you don't need to know them or you need to know them, because khalas, you already remember them. Because anything that is basically abnormal, like if it's not really ions, if it's like, for example, glucose or amino acids and lactate and phosphate, these are some organic compounds. These are big stuff. So you probably need them in the body unless there is an excess of them. So since you probably need them in the body, what is going to happen is that these guys are going to be filtered, or like reabsorbed, not reabsorbed immediately from the tubules into the body. Okay, because we need this glucose and amino acids. Because they're very important, they are the first thing to be filtered. So in the proximal tubule, throughout the length of the proximal tubule, the first thing that happens is that we're going to have the glucoses and these stuff filtered right back. And how do they move? They need a transporter that is going to use the sodium, right? So remember, now you see why we created this concentration gradient. This allowed us to have a low sodium concentration inside the cell. And because there is low sodium inside the cell, now the sodium wants to move into the cell. And it brings along with it the glucose or the amino acids. Now, once they're inside the cell, they can go through their own channel, a passive transport, and they can leave the cell into the body because we need them. Tamam? Now, one other point that I want to discuss is that sodium creates an osmotic gradient. What does osmotic gradient means? Whenever you're thinking osmosis, it is associated with water. The main ion that is going to be responsible for this osmotic gradient is sodium. So whenever you're thinking osmotic gradient, it's sodium and water. Sodium creates it, and then the water acts on it. If there is a high osmotic gradient, then the water is osmotic gradient is going to cause the movement of water. Tamam? If we're saying, okay, so what exactly do we mean by high osmolarity on like a solution? If there is high osmolarity, it means that it has, in a sense, a lot of, for example, particles or cells or like substances, for example, okay? So if there is a high amount of sodium, means there is high particles of sodium, means it is high in osmolarity. Or like concentration, just assume like think of it as concentration, tamam? So if there is low concentration of sodium, then there is low osmolarity, tamam? So what happened is that you see the sodium potassium ATPase, not only did it create an osmotic gradient here, but it also created an osmotic gradient here, right? Because the sodium is now moved outside into this area. So the osmolarity now is much bigger here. Now, osmolarity is important because it is associating the movement of water. Now, so just to understand, so you guys understand it from now and just to keep it with you for the rest of your years or like for the rest of your lives. So if there is a high osmolarity, if there's high osmosis or high powers, there's a lot of particles in there. How do you decrease their concentration? You put in more water. If there is more water, now this large amount of sodium wouldn't look as much. Like just imagine of it like there's an ocean or there's a pond or a small pool. If you put like, for example, 10 balls in a small pool, then you're going to have high osmolarity, high concentration. But if you put them in the entire ocean, no one's going to even see the pools, right? So that's what happens. That's the main idea behind osmolarity and the movement of these substances throughout the water gradient. Honestly, I'm not sure the difference between osmolality and osmolarity. I always just associate this concept with me and it works. So I'm really not sure about the meanings, but just think about it that way. Tamam? So again, this part here, I know I said a lot, but what you want to get out of it, and there is organic solutes that we're going to move because this is the first thing that we want to move. And then along with these solutes, because we created osmotic gradient on both sides, the first side moved the solutes, and then the second side is going to allow for water movement. Tamam? Because why water? Because remember here, wait 1 second. Which slide was it? Yeah, here. Yes, so water is very important. We need water in our body, but it's filtered على طول by the glomerulus. Glucose, amino acids, على طول كمان, these guys are filtered, but they're important to our body. So we're going to take them back. So we want to take them back from the start. We immediately want to bring them back to our body. So this is what happens, okay? So the first part of the proximal tubule. Remember, we're thinking of the early proximal tubule. So the closest to the glomerulus, we're taking back the most important stuff. One last point is that as the water is moving, what happens, because it still just came out of the glomerulus, right? So we have so many ions, so many stuff. So what happens is that the water, because there's a lot of stuff, accidentally it's going to take some ions with it, ions that are dissolved in the water, such as calcium, magnesium, and potassium. You don't need to know what ions are dissolved in water, but understand that since it's still at early on and there's a lot of ions that have been filtered, they will dissolve in the water. And as the water is moving, it will carry them with it because they're already dissolved in it. And this is referred to as solvent drag. Tamam? Easy part so far. Now, the next part here is this receptor that we crossed out because I want you to understand this idea of it. Tamam? Now, the only reason it's only mentioned here in this part is that I want to say that this sodium is creating an osmotic gradient, this same osmotic or concentration gradient that has been created by the sodium to allow the movement of the glucose and the amino acids. This same sodium gradient is also going to allow the exchange of hydrogen, right? Now, why I crossed it to this slide is because I want you now to understand what is the importance of the hydrogen. Tamam? Now, allow me, I'm going to go back to this previous slide just one last time, because I want to show you that glomerulus also going to filter out the bicarbonate. Now, what is the bicarbonate? You probably should know it, but bicarbonate is the base. And whenever there's a base, you know, there's an acid. Bases and acids are canceling each other. So if we are filtering out the base, then what are we going to, what's going to be remaining in the body? It is going to stay the H plus or the acids. Tamam? So we don't want to keep filtering out all the bases and not reabsorbing them, because if we don't reabsorb the base, then the body is going to become very acidic. And this is bad for the body. So you want to reabsorb the base to cancel out this acid. Tamam? So let's go to how exactly it happened. Again, since we're saying that it is something that is important to our body, then we're not going. I'm not saying that we're absorbing all of it, but we're absorbing most of the bicarbonate. Since it's important to our body, most of it is going to be reabsorbed where? In the proximal tubule, the first one or the closest structure. Tamam? So now, since we said that the body, okay, there's another point different to the point that the glomerulus filters the bases. There is like another different concept, is that in a general sense, the body, throughout physiology, metabolism, throughout the entire body, the balance of acids and bases ends up being that the body would produce more acids than bases. Tamam? So like in general, the body is producing more acids than bases. So instead of actually just filtering out the bicarbonate, we want to keep even more bicarbonate so that we can cancel out the H plus that is being made by the body. Tamam? So how does the kidney deal with that? There is two ways. It either can make its own bicarbonate and release it throughout like other cells in the kidney, or it can reabsorb it from the urine, because we don't want to get rid of it. So we're going to reabsorb it from our urine. So, okay, so this is an easier way, so we're going to do that. So how does this process take place? We'll start at this first step. I'm not sure if you heard of this process before, called carbonic anhydrase, but what it does, or it's basically an enzyme that wait, let me check if I have another slide for it. No, okay, I don't. So what the carbonic anhydrase does, it's an enzyme. It takes water and carbon dioxide and then converts these two to an acid and a base. Tamam? Carbonic anhydrase, this is an important enzyme. And from now, I'm gonna tell you it and just remember it. Even if you didn't get questions about it in the exam, even though I think it's important, but keep it in mind because it's really important. Tamam? Carbonic anhydrase takes water and carbon dioxide, joins them together to give you an acid and the base. Which one is the acid? This is the acid, and this is the base. Tamam? So it gives you the acid and the base. Now we said the body has more acid outside, or the body is producing more acid. Okay, so this is the body here. The interstitial space is the body or the blood. Okay, assume it's, for example, blood, because they're ending up in the blood. Tamam? There is more acid in there. So the first thing we do, we take this bicarbonate and then we're kicking it out and using what? Again, using sodium. Tamam? Sodium is very important in the transport of like almost everything, or a lot of the stuff are going to be dependent on sodium for transport. Tamam? So this is also going to help you when you're thinking about the lecture, or when you're trying to memorize the receptors for the lecture, because a lot of them are going to be linked to sodium. Tamam? And real quick, the most important receptor that creates this sodium gradient was the sodium potassium ATPase. Tamam? This gradient is not related to this because I know there's more sodium outside here, but here the body needs to get rid of the bicarbonate. Tamam? So we need to not get rid of it, I mean to send it to the actual body fluid, tamam, or to the blood. So that's why we use sodium and a co-transporter to move them together. One point, okay, let me just finish this process, then I'm going to talk about it. Tamam? Okay, so we sent out the bicarbonate. Now we have an H plus that remains. Do we want to send H plus also to the already acidic body? No. We need to get rid of this H plus and change it with the bicarbonate that has been secreted by the glomerulus. Tamam? So this bicarbonate here was the one that the glomerulus filtered. So how do we change this H plus? Again, look what you find. There is sodium. Tamam? So sodium, again, is important for the transport. So sodium is exchanging. It's going into the cell while the H plus is going outside the cell. Now, remember this H plus and the bicarbonate, they're the same ones found here. And this process, this time means it's interchangeable. So we have another enzyme, or the carbonic anhydrase enzyme, that does the same process inside the tubule. So the tubule is here inside the urinary system. So what it does is that it combines the bicarbonate and the acid to give you water and carbon dioxide. And now this is important because the carbon dioxide as a gas okay, the carbon dioxide can then pass through the cell through simple diffusion, because it's a gas. A gas is like, it can pass through the membrane. However, it's harder for ions to pass through diffusion because, you know, ions are charged, so they're going to be repelled by the membrane, so they can't really pass through diffusion. So that's why we couldn't, like, if you want to say, like, why can't we just reabsorb the bicarbonate immediately? Because it's an ion, so we want to convert it to carbon dioxide first, and now that it's a gas, it can go into the cell. And guess what? Once it's in the cell, it goes through carbonic anhydrase again, and now it's bicarbonate. So this bicarbonate that was here is now found here, and then it's secreted out through the same process. Okay. So what happens is you got carbonic anhydrase, got the H plus and the bicarbonate. H plus, we're sending it into the urinary system. I'm gonna refer for the urinary system as the tubular lumen, okay, to make it easier. In case like I say it later and like you get confused. So urinary system, I don't mean the kidney, I just mean like the system of the urine. So the ureters, the tubules, okay? So once it's released, it does carbonic anhydrase with the bicarbonate. Now you can reabsorb the carbon dioxide because there is already water in the cell. The water and carbon dioxide can pass through the cell, but already there's water in the cell, so we don't really focus on it. The main important point is the carbon dioxide. So, and then inside the cell, we make carbon dioxide, and now the bicarbonate is going to be co-transported with sodium outside the cell as sodium bicarbonate. And that's it. The point that I wanted to mention, it's not related to this, and it's just for making stuff easier for you. What is the charge of sodium? Sodium is positively charged. Let me see if I can erase everything on the screen. Okay, so sodium is positively charged. Bicarbonate is negatively charged. So if we're moving, let's assume we're talking about bicarbonate. So we're trying to move bicarbonate outside the cell. Tamam? So what happens is that inside the cell, we lost negative. So inside there is more positive now, and outside there is more negative. And if we're going to move sodium with it, sodium is positively charged. So what happens is that we want to cancel out these charges. So we move the sodium out as well because sodium is positively charged. And so what happens is that inside the cell, since we lost a sodium, it becomes negatively charged. And then the positive and negative will cancel each other out. So this is how you remember that sodium and bicarbonate, since one is positive, one is negative, both of them are going to move in the same direction. In the same direction. However, sodium and H plus, since both of them are of the same electricity or the same charge, what happens is that one of them, or like they're gonna move opposite to each other. One of them goes in and the other goes out. Why? Because they're both positively charged. So if we said that both of them go in, now we have two positive inside the cell and two negative outside. So this is bad. Instead, what we do is that we change them since they are of different charges. Tamam? So this is just also a general concept for all receptors in the body. To make it easier for you. Okay, now we just passed through the early proximal tubule, and what happened is that we took the sodium and created an osmotic gradient to reabsorb the water. Why did we reabsorb a lot of sodium? Because a lot of the sodium was reabsorbed with the substances such as glucose, amino acids, with the bicarbonate. So we absorbed these guys. Okay, and then we also absorbed the most important stuff to our body that we just mentioned. Now we got to the later part of the proximal tubule. Here's a nice thing. So, okay, now what happens in the later parts of your proximal tubule? We're still talking about the proximal tubule. We're moving down the long length of the proximal tubule. What happens is that at the start, we're getting rid of all the sodium from the urinary system. Okay, we're taking only the sodium, we're leaving everything else. So towards the end of the proximal tubule, since we took all the sodium and all the water, what happened is that the chloride has remained in the tubular fluid or the urinary system. Okay, so we're talking now about chloride. So think of it in a way that towards the end of the proximal tubule, what it tries to do now is to actually balance this loss of positive charges, or like to balance out this movement of positive charges. So think of it as the later part of the proximal tubule is trying to like fix up the small mistakes that the first part made. So what we're talking about here is the movement of chloride. Again, also it's going to be associated with the movement of sodium. So how is chloride going to be moving? The first thing we said is that so the water and the sodium were leaving that urinary system. So what's remaining there now is a slight amount of water with a lot of chloride because the chloride didn't move. So if there is little water and a lot of chloride, there is a much higher, or like a higher concentration of, okay, so we're talking here about the concentration of chloride. It's increased, tamam? However, since we didn't move any chloride through the body, the chloride concentration here is decreased, tamam? So sodium and chloride, as a result, they're going to travel down their concentration gradient because they go from area of high to areas of low concentration. So this is the first method of movement, tamam? So this is the first method of movement. They're gonna travel paracellularly, para is between the cells, tamam, due to the osmotic gradient, tamam? Now the other pathway is a little bit more complicated, but it's also easy, tamam? Don't worry about it, we'll go over it. Okay, so now we're talking about the late proximal tubule. So again, what is the most important receptor that we are gonna have in almost every pathway that we're going to discuss, because it creates the gradient that we need? This one, sodium potassium ATPase, tamam? So we started with the sodium potassium ATPase. What did the sodium potassium ATPase do now? It created high concentration of sodium outside and the low concentration of sodium inside the cell, tamam? Now based on that, sodium can now move into the cell. Okay, so what happens now? Sodium can move into the cell, and at the same time, inside the cell we have anions. Okay, so anions that either came, like they are found in the cell, or anions that were found in the blood that didn't get filtered. And then these anions, we're not talking about like anions as we're not talking about them as like chloride, for example, or like what is it called, like stuff from the atom, elements. Yes, we're not talking about elements or like structures that have negative charge. We're basically talking about bigger stuff. For example, let's say a negatively charged protein, for example, okay, or something that is big and negatively charged. So a negatively charged organic compound, not only like a negatively charged element, tamam? So if there were these anions or negatively charged compound in the blood that went into the cell, or now they're chilling in the cell, so we need to get rid of them, tamam? So there is a high concentration gradient of chloride here, صح? So it wants to move into the cell. This was the first way, and now this is the second way for the movement of chloride. It needs to be replacing with another thing. So there's two ways for it. Like if we want to think about it theoretically, tamam, it could either move into the cell with a positively charged substance, or move into the cell and then kick out a negatively charged substance. So what does it do in this case? It moves into the cell and then it kicks out a negatively charged substance. And this is important because in some cases, like these negatively charged substances, as I told you, they are big substances that are negatively charged. So we want, in some cases, to get rid of them already. So what this chloride or the anion transporter, it's helping us, tamam? So what it does is that it is going into the cell due to its concentration gradient, and it's kicking out these anions, tamam? Now some other anions, for example, that maybe they're just there, and it's not really important for us to get rid of them, tamam? So what they do is that now that we have anions here, and remember this sodium hydrogen transporter, so just real quick, I'm gonna mention it, tamam? So the sodium hydrogen transporter was mentioned in this part as well, because it's an important transporter that is regulating the sodium concentration and the sodium concentration mainly, tamam? Because there is different gradient now, tamam? However, I only mentioned it in this slide because I wanted you guys to understand this concept so that you can associate it now. Okay, so with that said, the sodium hydrogen transporter, just think of it as found there, okay? So the chloride anion transporter sends out this anion outside. This anion now, since there is a negative charge and a positive charge, usually what do? They combine it with each other and they create this H anion, for example. It's not a name, you need to remember. Basically, they create this neutral substance, and since it's no longer charged, it can, such as the carbon dioxide, for example, since it was no longer charged, it was able to move through the channel or through the cell. So since this one is no longer charged, it moves through the cell and then it breaks down to an H plus and a negative charge, and then it can repeat the process to help lower down the chloride gradient, tamam? Okay, so this is the entire concept. You need to understand about the proximal tubule physiology. So I got a question. When it kicks out the negative charge anion, it's like a replacement for the chloride. Exactly, because we lost a negative charge outside, so we want to put a negative charge outside to replace it, tamam? So that's why it's replacing it. However, if it was substance that we were thinking about positively charged, then both of them will move together because, a negative wants a positive always to balance it out. Okay, so this is all you need to know about the receptors. I'm gonna go through over this. Okay, let me leave it for later. We'll go over it later after we're done with all the proximal tubule. This is the most important concept. Okay, now One last point that we want to talk about is that throughout the proximal tubule, the glomerulus in general, it doesn't filter out proteins. However, some proteins, like a small amount, like for example, 5% of the proteins found in the body could leak into the urinary system. And if in the case that they are going to be leaking into the urinary system, what we need to do is we need to take them back into the cell, because proteins are important. They're similar to glucose, they're similar to amino acids. If we said we can't get rid of amino acids because we need to make proteins, so how can we get rid of proteins, right? So we need to reabsorb them. Now, this is important, is that the way proteins are reabsorbed is endocytosis. Endocytosis is that the cell makes a membrane around the protein and pulls it into the cell. And what is the importance? Or no, it's not that important. It's endocytosis. I want to mention it because we got a question about endocytosis in the TBL. So, okay, now you know. Proteins moved by endocytosis in the proximal tubule because they're important. So, endocytosis. And in the case that the proteins fail to be reabsorbed, or the body had some or like, why do proteins need to be reabsorbed? Because if we found protein in the urine, then this is a sign that there is a disease, okay? So if there's protein in the urine, this is a sign that there's a disease in the body. And because usually all of it is going to be reabsorbed. However, if the glomerulus filtered more proteins due to some damage in the glomerulus, then too much protein, we won't be able to filter out all of it. And this is going to be meaning that some of the protein will leave in the urine, and this will indicate disease. Tamam? So this quick concept, proteins reabsorbed by endocytosis. Yeah, the rest is just for understanding. Okay, so another point is that some organic anions and cations, and if this part, okay, just know it. No, there's other substances, important substances, anything other than small structures is going to be reabsorbed. For example, cyclic AMP, bile, hippurate, oxalate, whatever else, drugs. You don't need to know this stuff, by the way. Yeah, they don't come in questions. So these stuff, they could be positively charged, they could be negatively charged. Yeah, these stuff, since we need sometimes to get rid of them, sometimes to reabsorb them, or these ones are going to be mostly, yeah, we only want to get rid of them. So for example, drugs, after a drug is broken down, you're going to learn this in POD, pharmacology. So drugs, you can't keep a drug in your body. After you use the drug, it's a waste now, so you want to get rid of it. And then one way to get rid of it is through the kidney. So how do you get rid of it in the kidney? Through the system. So, okay, so these stuff, anything else, any big stuff, we get rid of them على طول بالproximal tubule. Clear? Now, this slide is important, and you're probably most likely going to get a question about this graph. And I got some practice for you on this graph, but okay, let's understand what's happening here. Now, there is, or what we're talking about is, this is through the proximal tubule length. So this is meaning like here is beside the glomerulus, and here is towards the end of the proximal tubule, where we're going down to the descending. So concentration, again, is going to be associated with concentration associated with water. Yes, that's what I'm talking about. Okay, so if the water amount is not changing, or the substance amount is not changing in relative to the water, then its concentration is not changing. Tamam? And if it's increasing or decreasing, we're going to talk about what happens, or what's the differences that are going to be occurring. Now, one other thing is that it's talking about the tubular fluid plasma concentration. I explained it in another past session. When you guys get any type of fraction like this, all you need to really focus on is or like any ratio, just focus on the numerator or the first element. If we're talking about the tubular fluid concentration, then we're talking like any increase means that there's more in the tubular fluid, less in the tubular fluid. Okay, so now this here is just a simple fact. We said the proximal tubule is reabsorbing the most important stuff. So we got the water, we got the bicarbonate, we got sodium, we got chloride, potassium, phosphate. It always reabsorbs 67% of these substances. Okay, now let's look at the graph and try to understand what's happening here. At point 1, we said this is related to the concentration of a substance and water. If the water is like not changing, so at point 1, this is the balance where the water amount and the substance amount inside the urinary system and outside is the same. Okay, now let's take some substance such as sodium or chloride or urea. These guys that are around the gradient of water. What does this mean? It means that these substances are moving outside the cell, right? We said that they're going to get reabsorbed and secreted. Okay. However, as they're going to be reabsorbed, they're going to be reabsorbed with the same amount of water, right? So if we said, for example, you're moving like, or like just, okay, so the same amount of water that has these substances they have this concentration. Now we move this water and this sodium chloride and urea, we move them all to another place. So what happened is that we only change the place where they're sitting. However, they are still the same substance, and that's why they are close to the osmolarity of water, or they're close to level 1, because they're not changing. Now, if we take something, however, such as glucose and amino acids, if you look, they're going very down. Why is that? What exactly is happening here? What is the mechanism? Like, what's the idea? We said glucose and amino acids are going to be reabsorbed, right? However, so we said 67 here. However, 100% or 99% of the glucose and the amino acids are going to be reabsorbed, even though 67 and so 100% are reabsorbed, while 67% of the water is reabsorbed. So we said this is the amount, tamam? And then we reabsorbed this entire amount, but we absorbed only a small bit of water, tamam? So what happened is that their concentration is going to be increasing. Yes, increasing in the plasma. Okay, so the difference is that, yes, they're increasing, but compared to the urinary system, since we're taking all the glucose from the urinary system into the plasma, there's no more glucose out here. So it's going down to a level near the 0, okay? Because there's no more glucose in the urinary system, okay? And then if we take something such as creatinine, which you guys probably know from your first lecture, creatinine is a substance that is going to be completely secreted. We don't reabsorb it. So what happens is that the same amount of creatinine that was in this area, or this is the urinary system, we have this creatinine and this water. We didn't change the creatinine, but we changed the water. So now the concentration of creatinine is higher in the tubular fluid. So that's why it goes up. Okay. This is practice. Oh, wait, hold up. Wait, I wanna just blank out. Oh, never mind. I was gonna blank out a certain part. Oh, okay, so why is it not blanked out? Okay, yes. This was for you guys to practice. Please try and answer in the chat with me. Tamam? We said we reabsorb 65% of sodium with 65%. Okay, so our base, the substance that we're wait, hold up, let me just hold up the pen. Our basic water amount that's creating the concentration gradient here, water, is at 65%. Tamam? So sodium is reabsorbed at 65%. On the graph, is it going to be A, B, C, D, or E? Which do you guys think? A, B, C, D, or E is for sodium? Okay, C. You're right, because it's absorbed at the same amount of water. So bicarbonate is absorbed 85%. So is it going to be A, B, C, D, or E? D, correct. 90 and 100% of glucose, amino acid, and other organic substances. E. And then the sodium, again, we discussed it. Bicarbonate, we discussed it. Chloride, which one is going to be chloride? If we said 45% of chloride is going to be reabsorbed. B, correct. And then last one is inulin. Inulin is like creatinine. I think it was mentioned in the first lecture, which is A. Okay, you're right. So you guys got this concept. So this last slide here, there's nothing to it. I just want to show you guys that sodium is really important in the movement of everything, in chloride, calcium, 8 amino acids, H+ is moved with sodium, glucose, phosphate. So everything is really kind of associated with the movement of sodium. Okay. Checkpoint. Do you guys want the checkpoint? Or do you guys want a break? Okay. Let's go to the second part, within descending limb. I'm gonna just real quick, I'm gonna go over the proximate tubule one last second so that I show you guys the important stuff or the main key points. So the proximate tubule is eliminating the most important stuff at the start at the price of sodium, and this is created by the sodium potassium ATPase gradient. And then we move the water, we create the solvent track. Then this carbonic anhydrase experiment in this equation, even if you didn't get questions about it, it's important that you guys understand what's happening because it will help you a lot in the future. Tamam? The main important thing that we're trying to do here is that we're trying to get the bicarbonate back into the actual body. And then towards the end, or the proximal tubule, now we can move the anions, and this is going to be done, sodium potassium ATPase and the chloride anions receptors. Okay, so proteins endocytosis, we got a question about it, so you guys better focus on that. And then this graph, inshallah, it's all clear. And let's go to the second part. Now, from now, inshallah, everything else will be easy. So let's go. Second part is the descending limb. So about here. Remember in the first slide, we said that in the descending limb, what happens is that only water is going to be reabsorbed. Tamam? So in the descending limb, only water is going to be reabsorbed. And the channel that is responsible for the movement of water is going to be aquaporin 1. Now, later on in the lecture, I will discuss, like towards the collecting duct, we are going to have aquaporins 2, 3s, and 4s in different channels. So since we're going to talk about them later, I'm going to say it right now. So a way that you're going to remember that aquaporin 1s is in the thin descending limb, and it's not aquaporin 2, 3, or 4, is that the first thing that we're going to have is the thin descending limb, right? So since it's the first structure, we're going to have aquaporins 1 with it. Tamam? So aquaporin 1 takes in water, but it doesn't take sodium chloride, okay? It only takes in the water. Now, then we got the ascending limb. The ascending limb is the opposite. It takes in the sodium and chloride, but it doesn't take in the water, tamam? So the descending limb and the ascending limb, the loop of Henle, are different. So one takes in the water, one takes in the salt. And since there is no water reabsorption, okay, so that's it, okay? So the difference between the thin and the thick part of the descending limb, of the ascending limb, is that the thin part allows for passive transport, and the thick part allows for active transport. So using ATP. Okay, so how do you guys want to remember it? Or like, how do you remember that the descending limb is taking out the water only? Because what do you guys think is more important, having more water in the body or more sodium chloride? It is, of course, having more water, because you know the sodium chloride is there, and as we said, it is being reabsorbed and being secreted at the same amounts, kind of. But the water, if you don't have the water, you're gonna have high hypotension. So we want to get the water back first. So that's why the descending limb reabsorbs water, and it's the first thing because it's more important than sodium chloride. Tamam? And then later on, you got the sodium chloride. And how you remember the passive and the active? And the first one is passive, or because it's closer to the descending limb, and they're both thin. So the thin is always passive in the general sense, so you can think about it. Or thin guy is a small guy, so they can just pass through it. Tamam? These are different ways that you can remember them. Now, the thick ascending limb, we said it is going to be done through transporters. So let's discuss them here in a second. Inshallah, it's going to be easy. Tamam? So the first thing we said is going to be your sodium potassium ATPase. In everything, sodium potassium ATPase. Now we have a concentration of sodium gradient that is going to be different. Tamam? High sodium outside, and the low sodium inside. Now, this time, the high sodium outside here, the sodium is high here. Now, what it does, it activates a new channel, the sodium, potassium, chloride channel. Okay, how do you want to think about it? Is that, okay, now how do you know that we're now talking about sodium, potassium, chloride? Is because we said the first part of the proximal tubule was removing only the positive charges. And then the second part corrected that mistake and removed the negative charge. Now, what we're trying to do in the ascending and descending limb, we don't want to make any more of these mistakes. And that's why we're going to take in the positive and the negative charges. Okay, so that's how you remember that the ascending limb now has the sodium, potassium, chloride channel. Okay, so what we're trying to do, again, as I said, we're trying to move the sodium and the chloride. So we got the chloride here, we got the sodium here. Okay, so potassium can just leave through its channel. Chloride can leave through another channel because we want to move it with the sodium chloride. Now, the last point that I want to mention is that this chloride now, what happened is that some of it can move back inside or to the lumen. But as you can see, just a small amount. However, this small amount, so right here we got 2 positive, 2 negative charges. So we crossed out the electrical charge. But the potassium moving back, it's creating a positive charge, right? So positive and positive are going to repel. So as you can see, sodium, magnesium, potassium, and calcium, these are some positively charged ions. They're going to be repelled, and they're going to pass between the cells because of the negative charge due to the electrical gradient, and they're going to pass into the blood. Tamam? So I think this is clear now, and inshallah, you guys will not forget it. Let me just make sure that I didn't miss anything. So some potassium leaks back, and because of that, we're going to have the cations moving paracellularly. All right. But this was brought from the lecture slide. This is talking about the same thing. Again, sodium hydrogen is found everywhere. Carbonic anhydrase. Khalas, you guys know the concept of it. Carbonic anhydrase, sodium hydrogen exchanger. Then you got the sodium potassium pump creating the gradient, and this part, of course, from the sodium carbonic anhydrase. Then we got this guy and the potassium chloride. However, some potassium leaks, just a small amount, allowing for the movement of these guys. And the reason is I added this picture is that I want you to remember, or if you look at something and try to remember it, then I want this picture to remind you that the ascending limb, it repels water, because even though it is a thick ascending limb and it is having active transport channels, however, it's still a part of the ascending limb, and both parts are only taking sodium chloride, but not the water. And because it is repelling water, it is referred to as diluting segment. So dilution is opposite of concentration. Because there is more water here in the urinary system, but less ions, what happens is that there is going to be a lower concentration of these ions. So there's going to be more water, like it's going to be diluted. Okay, so because of the water, the increase in water and decrease in ions. Okay, so the next, okay, this part, it's not in the lecture, it's going to be in the next lecture, your urine concentration and dilution lecture. However, I'm just going to be immediately, like, for like 1 minute discussing here what exactly happened and what is the effect of the descending and the ascending limb in this concentration picture. Tamam? So throughout the urinary flow, we said in the descending limb, only water is leaving. Tamam? So if we're keeping the substances and we're kicking out the water, the concentration towards the end is going to be very high. Tamam? And why does the water move? Because in the medullary interstitium, tamam? And again, if you remember, I told you that the urinary system is surrounded by the medulla, like not the medulla, but the kidney tissue. Tamam? So this part here, all this space that you see is actually kidney tissue. Tamam? So this is referred to as the interstitium, or like inside the cell. It's divided into the cortex, outer and inner medulla. It's referred to as the medullary interstitium because the descending and the ascending limb are in the medulla division. They're not in the cortex. Tamam? These parts are in the cortex, but these are in the medullary division. So there is an high osmolarity. If we say high osmolarity here, we mean this area there is so much osmolarity. So water is going to move into this area in order to lower the osmolarity. However, in this part, what happens here now is that we're only moving the ions, but not the water. So the concentration out here is going to be decreasing. Now, this is just the concept I wanted to explain to you here, so that when you get the lecture, you can understand it. Then they will explain to you how exactly we got these numbers and what is the significance of that. So this is not part of this lecture, okay? Now we're going to the fifth stop, which is our early distal tubule. So we just finished the proximal tubule, early part, late part, and then we got the descending, then we got the ascending limb, and now we have the distal tubule. Now the early distal tubule is similar to the ascending limb. Okay, so it's still coming up newly. It didn't change its habits. It's similar to the ascending limb. Okay, so we got the sodium potassium ATPase. What do I mean by that is that there is no water transport. Tamam? So it's similar in the sense that there is no water transport. And then we got even it is simpler than the thick ascending limb. Tamam? Because we said we're trying to reabsorb sodium chloride without water. So there is no water. We create the gradient with this sodium potassium ATPase, and then we have a channel for sodium and chloride. Since they're opposite charged, they're moving together. So they're moving inside and then they're moving out. Tamam? And then there is the calcium also. Calcium can also move with this guy through a calcium ATPase. Okay. Now we didn't discuss in the previous slides about calcium. Why? Because calcium is found or is going to be reabsorbed in the proximal tubule, in the ascending limb or ascending loop of Henle, and in the early distal tubule. Now the difference is that in the proximal tubule and in the thick ascending loop of Henle, the movement of calcium is going to be paracellularly. Paracellularly means it's going to move between the cells, so it doesn't really need energy. It, like for example, it could move with an osmotic gradient, or it could move with the electrical gradient that was created, or with the solvent drag that was making the water carrying these stuff. So they're moving paracellularly. However, this paracellular movement is the main movement, because early on we try to get these stuff back. So when we get to the distal tubule, only a small amount is left of calcium, and we try to reabsorb this amount. However, in the early distal tubule, the reabsorption is transcellularly. As you guys saw, it needs a channel to allow it to move. So it's through the cell. How does this transcellular transport occur? Okay, this is the paracellular transport. How does this transcellular transport occur? Calcium just moves into the cell, and then you have a calcium sodium exchanger that is going to move, or a calcium sodium exchanger that is going to pump calcium outside the cell. Again, we see here sodium potassium ATPase is really important. Why? Because this sodium potassium ATPase is what drives the transport of everything. So since here we now see we have a low sodium concentration here, And this low sodium allowed us to move the sodium into the cell and the calcium outside the cell, right? So this is how we move the calcium out. This is the first way. The second way is that, remember in the carbonic anhydrase slide, I said that the body, in general sense, it makes more acid than base. So here we have higher H+, tamam? So similar to the sodium way, just that it's outside now, it is going to go into the cell and exchange of calcium, tamam? So calcium is going to be pumped by the sodium or by the H+, tamam? One last point that I want to say regarding the paracellular transport, tamam? Paracellular transport depends on sodium movement. So in the proximal tubule and in the ascending loop, wherever sodium is moving, calcium is following sodium, tamam? So if sodium is moved from the lumen of the urinary system into the blood, then the calcium goes to the blood. If the sodium stays there, the calcium stays there. So it's just sticking, just like the younger brother of sodium, following it everywhere. However, in the distal tubule, it's not associating itself with sodium. It's moving on its own. This is a checkpoint. Allow me just 1 second. I'm going to pause the recording because Ahmad just took my laptop charger and I'll be back. Just a second. All right, so let's begin where we stopped. So we now will talking about the late distal tubule and the collecting duct. So the late distal tubule and the collecting duct, this is towards the end of our duct or the tubular system pathway. So what's remaining here is only the few stuff or the few remaining particles, the few remaining water, electrolytes. And what we're trying to do in this part is that basically fine-tuning, modifying, and regulating. And since we need to know what's happening in there, we need the hormones, as they are going to be the only way of communication with these tubules, so that we know that, oh, well, we need to reabsorb the sodium more, or reabsorb the water more, or we need to get rid of it. Now, the beautiful thing, or like the people that might, like the nice thing about them that might be a little bit tricky, is that these two parts, they have two different types of cells, intercalated cells and the principal cells. Tamam? So, and now we're going to discuss the function of both types of cells. So the first one is the principal cells. The principal is basically like, you can think about it such as like a principal, you know, it's like the main guy. So the principal cells, they're doing the main function. So what is like the main or the important thing here for us? It is the water and the sodium. Tamam? So, not sodium, but like electrolytes in general. Tamam? So the principal cell is regulating the water and the electrolytes. So what happens here is that, let's start with the first part, or the electrolytes. So what happened is, I apologize for the drawings, but I accidentally explained it without completing the continuing the recording. So I'm explaining it again now. Tamam? Okay, so aldosterone, ignore this part now. But the only reason aldosterone is mentioned here as well as the ADH, because as we said, they are the form of communication between the two cells. The aldosterone is for the sodium, the ADH is for the water, and we'll discuss them in a second. But now just focus on the mechanism, what happens. So as we said, all throughout the tubular system, sodium potassium ATPase creates the gradient. Now there's more sodium out, more potassium in. So let's talk about the sodium. If there is less potassium inside the cell, so the sodium now here is going to move from area of high concentration to an area of lower concentration inside the cell, right? And it does that through a channel referred to as the ENaC. It's not a specific name of a channel. It's not really any important name. All it stands for is the epithelial sodium channel. So it's not an important name you need to know. Just know there is a sodium channel that moves the sodium into the cell. Tamam? At the same time, we got more potassium here. And then, so what happens that there's not that there is less potassium here, but no, less potassium here, but no, potassium didn't move to this side. Potassium only moved inside this cell. So as a result, it's going to move, probably due to a concentration gradient, into this part here. And this is done by another channel, ROMK. You don't need to know the name of the channel again. I've got this picture from an outside, so it's not in the slides. You don't need to know the names. Tamam? So a potassium channel pumps potassium into this part. Tamam? Now, the sodium channel here, or the sodium pump, is pumping sodium more than the potassium channel is moving sodium into this area. As a result, what happens is that we're losing positive charge faster than we're gaining it back. So there's going to be a net negative charge. And this net negative charge is going to push some chloride ions between the cells or paracellularly into the interstitium. Now, one other point I want to discuss is that the principal cells, or the cells in the distal tubule and the collecting duct, and حتى the intercalated cells, these guys are very close to each other and they're tighter than the other cells in the other parts of the tubular system. As a result, they allow only minimal or very little paracellular transport. So like chloride, indeed it can pass, but it's a dashed line because very little chloride can pass. And at the same time, very little of other substances can pass. And why is this an important point that we need to understand now? Because sodium has moved from this area into this area. So sodium is now here. And sodium is responsible for creating the osmotic gradient. So now there is high osmolarity here. So as a result, the water wants to move from this area into this area in order to balance out this osmotic gradient or the concentration gradient or the high concentration of sodium that was created. Now, because there is no paracellular transport, the main way for us to do that is going to be through channels. Okay. Now, we said in the descending limb that we have aquaporin 1s, because it comes first. Now, throughout this, because it's later on in the pathway, we got aquaporins 2, aquaporins 3s, aquaporins 4s. Okay. Now, it's not necessarily that because it comes first, or like it's just the way that I said it so that you guys can remember it. Okay. So where each one is. Okay. So aquaporin 2, what it does is that it is the channel connecting between the urinary system and the rest of the body, or the principal cell, or like the blood, and maintaining this stuff in the body. So it is the main regulator. As a result, if ADH is going to bind, the ADH stands for antidiuretic hormone. So antidiuretic, anything that has diuretic in it is referring for urination, so increasing urination. So an antidiuretic wants to prevent urination. And when we say prevent urination, mostly talking about, we don't want to have a lot of fluids in there. So fluid is water. So antidiuretic hormone doesn't want a lot of water and it wants to reabsorb the water. So how it does that is that by it creates like protein synthesis after it binds on a V2 receptor. It creates protein synthesis inside the cell. And this protein synthesis allows us for a protein synthesis of what protein? The aquaporin 2 protein. And then it's going to be integrated into the membrane. And this allows for water movement. Okay. The aquaporin 3s and aquaporin 4s then move it to the blood, but these guys, they're not affected by ADH. They're going to be found there in both ways, whether there is aquaporin 2 or no aquaporin 2. But the presence is controlled by ADH. One point that I want to mention, but it's not probably not important for you guys, but it's fun to know. But you will need it next year. But for this block, you don't need to know it. Is that ADH can act on V1 or V2 receptors. If it's going to be associating with the kidney system and the water, it is going to be binding on V2, because ADH also has another name, which is vasopressin, and that's why the V comes from, or that's where the V comes from the other name, vasopressin. So since it's vasopressin, it's constricting or pressing on the vessels to close them down. If it wants to do that on the vessel, it is going to be on V1. And a way to remember, how I remember it, is that since it's vasopressin, so vaso is for vessel and pressin is function, is like constricting the vessels. So V1, or the number 1 function, is doing what the name says, which is compressing. Or V2 then is going to be for the kidney and the water. Right? Other part, which is the intercalated cells, this one is going to be responsible for the acid and base regulation. Again, similar to everything else that we mentioned before about acids and bases. Carbonic anhydrase, bicarbonate leaves through its channel, H+ leaves through its channel, and then we got the other H+, even more that we could get rid of this H+, through a key H+ potassium ATPase exchanger. And how do you want to remember that there is this potassium here? So since these principal cells and the intercalated cells are found in the distal tubule and the collecting duct together, between multiple, for example, principal cells, you can find some intercalated cells. So they're sitting beside each other. They're connected with each other. So when the principal cells is releasing this potassium, it's actually going to be used by the intercalated cells to move in, or to move in exchange with the H+. And this also contributes to why we have a negative charge here, even though we're moving positive ions in both directions. But this helps us contribute to the negative charge that causes the movement of chloride. So intercalated cells are just moving acids and bases. Okay, so guys, can we start now? You guys are here for the ones attending. Okay. Apology if I clicked ask to unmute. All right, so let's go to the hormones. Now, plus we discussed them. Aldosterone, this is gonna be more renal knowledge for you. It's not specific for the lecture. But this part is not mentioned with you. However, I'm going to explain it now because it's important to understand. So aldosterone is a steroid hormone, and we have multiple other steroid hormones. Now, this is related to a clinical disease that we'll discuss in a second. So steroid hormones, basically multiple steroid hormones. One of them is aldosterone and cortisol. It is used, or the name is used interchangeably in the lecture. So I remember last year for me, I got confused whenever I'm seeing them. So I'm putting here the names so that you guys can, like, خلاص, from now, you won't get confused if you read the actual lecture slides. But inshallah, this will be more than enough. You don't need to go through the lecture. So mineral corticoids is for aldosterone, and glucocorticoid is for cortisol. Later on in endorepro, when you learn about it, you'll learn that the function of cortisol is associated mainly with glucose. So that's why it is referred to as glucocorticoid. And a way to remember it is that cortisol is a stress hormone. So when you're in a stressful situation, you're going to have a lot of cortisol. So if you have a lot of, or if you're in a stress situation, you want glucose because it's your energy. So that's how you remember that cortisol is a glucocorticoid. While aldosterone is the mineral corticoid because it's associated with minerals. What are the minerals? Yani sodium and potassium, as we discussed in the previous lecture, previous slide for the functions of aldosterone. Tamam? Now, the release of the aldosterone is stimulated by high potassium concentration, because what's the function of aldosterone? It gets rid of the potassium, or through the renin-angiotensin-aldosterone system. I'm going to go over it as because it's important, but it's not part of the lecture. Kidney releases renin. Renin activates angiotensin, angiotensin 1, or the liver releases angiotensin, gives angiotensin 1, angiotensin 2, and then, so this is the A, and then you got angiotensin 2, which can vasoconstrict by itself or release aldosterone. And once you have the release of aldosterone, this is the part that is important for us here. What does the aldosterone do? It decreases sodium and water reabsorption, and it secretes potassium and hydrogen. Okay, this is a point that I didn't mention here, and I forgot to put it in the slide. But okay, wait, I have another picture. Yes, here we go. Okay, tamam. So functions of aldosterone. We did discuss when we explained the principal cells. We discussed that this part here is affected by aldosterone, which is the sodium channels, and I didn't. Okay, wait, I said to skip that part. So okay, never mind. Let me go over it again because I said to skip it. But I think you guys get an idea of it. So what is the function of aldosterone? Aldosterone, what it does is that it is increasing the process, like mainly, like the main function is increasing the activity in the principal cells. Okay, so aldosterone is released in a situation where, according to the renin-angiotensin-aldosterone system, we have low blood pressure in the body. If there is low blood pressure, we want the sodium, because the sodium, like aside from everything vasoconstricting, the sodium creates an osmotic gradient that calls in the water from this urine into the body. The water then becomes plasma. So if there is plasma, means we're in any plasma, there's more fluid or like more volume inside the vessels. So that leads to a higher blood pressure in case of hypotension. Tamam? So aldosterone is released in cases of hypotension, which would lead to the angiotensin or the RAS system, or in cases of high potassium. Why? Because the function of the principal cells, or the aldosterone, I mean, is acting on the sodium potassium ATPase. And we said this is the main guy. If it acted on the sodium potassium ATPase, what happens is that there will be more potassium secreted and more sodium reabsorbed. However, at the same time, it also stimulates the sodium receptor, because we're not only trying to like balance ions here, we're trying to increase sodium inside the blood so that we can have water following it. So we want to increase the sodium moving, or the sodium like movement, increase the speed of the sodium movement. That's why aldosterone, that's how you want to think about it. It starts with the sodium potassium ATPase, and then more sodium by acting on the sodium receptor. Now, another function that it does, but it's not really related to the main function of balancing blood pressure, but it is there, is that it acts on the intercalated cells, because these guys are beside each other. So it also acts on there, and it causes more H+ release. Basically, aldosterone, all it does is that it stimulates the intercalated cells and it stimulates the principal cells. So whatever these guys are doing, aldosterone makes them do it better. This is all you need to know. Yes, so this is the final function. Everything is done better by aldosterone. So if there is more aldosterone, then there is more sodium channels. This graph is done. More aldosterone, more sodium. If there is more potassium concentration, we said aldosterone release or is dependent on potassium levels. So if there is more potassium, the way that we want to get rid of more potassium is by having more aldosterone. So plasma aldosterone level is increasing. So more potassium, more aldosterone. Okay. And this slide here, and it's not similar to the mole one where you had to actually learn what's changing. But let me just hold up a pen. Yeah. So I'm talking about the mole hemoglobin one. But see, all it says is that it is. You don't need to think about it. You understand it. This is talking about potassium excretion. If there is more potassium in the blood, what does this mean? More potassium is going to get filtered out. Less aldosterone is going to be released. So we're going to be excreting more potassium. If there is more aldosterone, what does this mean? Aldosterone is going to increase the excretion of potassium. If there is more ADH, what is ADH doing? It is blocking the pathway of the water, and in the distal tubules, in the late distal tubule and the collecting duct, all these guys are increasing the potassium excretion, because more ADH and more water, and more sodium there, and potassium, so it's going to be excreted. Oh yes, because ADH, antidiuretic hormone. So what is an antidiuretic? It prevents diuresis or diuresis. There's no. Yes, there's wait. Okay, so yes, increased ADH means that the sodium is going to be reabsorbed more. Yes, so it's not allowed. ADH is going to be taking in more water. So this water is going to drive more sodium with it because of the higher water that's going to be found in the plasma now. And because more sodium is going to go with it, we're going to have more potassium being kicked out by the aldosterone system. Come on. Okay. And basically, these guys increase aldosterone, increase potassium excretion, so I don't think you're going to get a question about it. Hyperaldosteronism. Okay, I'm going to leave it here for a second. What do you guys think is going to happen when you have too much aldosterone? If we have too much aldosterone, first of all, we said there is going to be more sodium excretion and more low potassium. Yes, correct. And low H+. Tamam? So that's exactly what's going to happen. If there's more sodium in the body, more sodium in the body, if there's more sodium moves the water. Now there is too much volume, too much water edema, and hypertension. There is this potassium. Potassium is associated with weakness, constipation, changes in ECG. If there is alkalosis, or because we lost the H+, now there is alkalosis. So that leads to tetany, that leads to cramps. You don't, just understand these guys. You don't have to actually sit down and memorize, and wallah, hypokalemia causes muscle weakness. Just understand in general. Sodium, you already know it. But hypokalemia changes stuff. Alkalosis changes stuff. Honestly, I don't remember. I don't know them. I don't think we get questions about them. But no, خلاص, just know them. Tamam? In case. Okay, now the other disease here that some of you might find confusing, but it's really easy, inshallah, after we explain it, is the mineral corticoid excess syndrome. Okay, what is mineral corticoid? This is the aldosterone, because this one is confusing between the glucocorticoids and the mineral corticoids. So both of these guys are steroid hormones. Tamam? So when these guys are absorbed into the cell, they're going to bind on a steroid receptor. We have a glucocorticoid receptor and we have a mineral corticoid receptor. So theoretically, each one should bind on its receptor. But the problem is that the steroid receptors are unspecific. Tamam? So for example, like what is important for us to know is that the mineral corticoid receptor, the one that is responsible for binding aldosterone, is not specific. So it could bind either aldosterone or it could bind cortisol. Tamam? And it doesn't know that, oh, I'm binding cortisol or, oh, I'm binding aldosterone. It knows that I've been activated. Now my function is reabsorb sodium, get rid of potassium, get rid of hydrogen. Okay? So we don't want that, because if we're doing that, then basically what we're saying is that we have hyperaldosteronism. So the previous slide shows all the symptoms that's going to happen. So the body defense mechanism against that is through an enzyme, and it's a very important enzyme that you need to remember the name. 11-beta-HSD2, or hydroxysteroid dehydrogenase 2. What this enzyme does is that it breaks down the cortisol into something that is inactive, which is cortisone. Tamam? So in cases of deficiency of this enzyme, in cases of deficiency of the 11-beta-HSD2, what happens is that in case of deficiency, what happens is that cortisol is no longer going to be deactivated, and usually in the body we have more cortisol than we'd have aldosterone. So cortisol binds on the aldosterone receptor and causes the hyperaldosteronism, which is referred to as mineral corticoid excess syndrome. I'm gonna go over ADH, then I'm gonna guys show you. Oh, we got a checkpoint after that. So this is for aldosterone. ADH as we discussed, this slide added extra for you to show you. So permeable, or like this is talking about water permeability. So at the start, we said water was moving easily in the proximal tubule. That's where most of it is reabsorbed. Then the descending limb, only water. Now the ascending limb is going to be in the early distal tubule, and the ascending limb are only for sodium chloride, while the late distal tubule and the collecting duct are variable. Water permeability is variable. It depends on the presence of ADH. Tamam? So this is what the slide says. What are the stimulus for releasing ADH? Hyperosmolarity means there is too much sodium, so we're gonna have ADH in order to reabsorb the water into the body. Or volume loss means there's small amount of volume in the body, so that activates the renin-angiotensin-aldosterone system. It also activates the ADH system because we need the water. We don't want to urinate more if we have low volume in the or low water in the body. So more water reabsorption through the ADH. Do you guys have any question about hormones, or clear, inshallah, or anything else that we discussed? Okay. Now electrolyte, we discussed already potassium slide. I just put it in here again, so that because we're talking about potassium first. So what happens here is that again, we said more sodium, more plasma, more aldosterone, more ADH, and all of these guys are related to kind of having more potassium excretion. Potassium transport, this is a simple concept. When you are eating a high potassium diet, so you have more potassium in your body, therefore you want to get rid of more potassium. Tamam? And if we have high potassium in our body, what is it going to do? High potassium, remember we said it activates aldosterone. Yes, high potassium activates aldosterone. And if we activate aldosterone, that's how we're going to be activating the collecting duct and the distal tubule to release the potassium. So we can see here there is an increase in the secretion of potassium in the distal tubule and the collecting duct compared to these two in the cases of high potassium diet. Other point here is this is referring to this slide of the lecture. I'll just go over it and inshallah make it easy. So what we're discussing here, this is not effects. This is basically talking about causes of hyperkalemia, which is too much potassium, or causes of hypokalemia. So we're not discussing effects. So let's, it's very simple if we think about it. Hyperkalemia means we have too much potassium in the blood. Okay. What is the reason of having too much potassium? Either one, we're not excreting it in the urine, or we're eating food with high potassium. Ignore the acidosis in a second, I will discuss it. Or we have decreased aldosterone, because what is the usual function? Excreting potassium. So if we're not excreting potassium, we're going to have hyperkalemia. Tamam? Or it could be due to acidosis. Now, what is the reason of acidosis? Because in previous slides, if you look, there was a channel that said that H plus and K plus are going to be exchangers, or like exchanged by each other. Tamam? Other than that, just in general, throughout the body, H plus and K plus are increased, are exchanged. If we have acidosis, means extracellularly we have high amount of H plus. So if there is high amount of H plus, it wants to be exchanged to go into the cell, so that we're going to have a lower amount of H plus. And this exchange is going to be done with potassium. Okay, so H plus goes inside, and since they're both positive charge, the potassium goes outside the cell, and that's how we get hyperkalemia, or more potassium outside the cell. Hypokalemia is the complete opposite. If we said acidosis does this, then alkalosis, or like when there's too much basic environment, we cross out this process because we want H plus to stay here. As a result, K plus stays here, so we get hypokalemia. Or it could be because we're urinating too much potassium, or it could be because we're not eating food with potassium, or we could be vomiting or diarrhea, basically. So as a result of vomiting, diarrhea, you're going to get rid of fluids, and including these fluids, you're going to have potassium that's going to be removed. Aldosterone, too much aldosterone refers to the function of aldosterone. Thyrotoxicosis, I put as it was in the slide here, thyrotoxicosis, which is cell shifts, and insulin and catecholamine. So I got you guys this picture. Understand how it does that, because these guys, what they do is that they increase the activity of the sodium potassium pump. And once they increase the activity of the sodium potassium pump, what happens is that 3 sodium goes outside the cell and 2 potassium go into the cell. So we have more potassium going into the cell. So we end up with less potassium outside, which is hypokalemia. Now, do you really need to know all of these details? Probably not. just, I mean, at this point, I think you guys already understand them. So there's no point of me saying that there's no need to remember them because you understood them. The things that might have been confusing was the cytotoxicosis, how to remember it, and the cellular acidosis. But inshallah, with these two pictures, and you already know all these reasons. Tamam? And with acidosis, I just didn't write it, but there is ketoacidosis, lactic acidosis, and any acidosis is associated with the same concept. Tamam? Okay. The last part, this is the last slide, which is calcium. Calcium regulation is by 3 hormones that you don't really need to go to details now, but okay, just let's go over them real quick. First one is parathyroid hormone. Parathyroid hormone, what it does is that it is going to be increasing calcium reabsorption, and it does it. Okay, there's 2 hormones for increasing calcium reabsorption or increasing concentration in the body. Parathyroid hormone and vitamin D. That's why they tell you to drink vitamin D, because it increases the calcium in your body. Tamam? And another name for vitamin D you might get is calcitriol or 125 dihydroxycholecalciferol. So these are names for vitamin D. What these guys do, they increase calcium reabsorption. Tamam? So okay, so that's what the guys do. Increase calcium reabsorption. What decreases calcium calcium concentration in the body, or more excretion of calcium? It is another thing called calcitonin. Tamam? So calcitonin is going to get rid of them, while vitamin D and parathyroid hormone are going to increase the calcium concentration. Okay, I had a way to remember how this one was excretion, but honestly, I don't remember. I don't remember what it was, but you try to find something that will help you remember that calcitonin causes excretion. Again, this is the same slide here. I showed that there's also, he mentioned in the lecture that alkalosis, plasma phosphate, and ECV reduction. Now, I'm going to explain them to you so that you don't have to memorize, but it's going to be understanding. So plasma phosphate, what does phosphate do? It's details that is not important for you guys because you need it in endorepro. But parathyroid hormone is stimulate or is associated with calcium and phosphate. It increases calcium and decreases phosphate. So if you have too much phosphate, you're going to have too much, or you're going to have an increase in parathyroid hormone to get rid of this phosphate. And as a result, you're going to have reabsorption of calcium. So this leads to calcium reabsorption. Tamam? So the main mechanism, I'm gonna just repeat it one last time, is that there is going to be increased release of parathyroid hormone. ECV reduction, this is referring to the volume in your vessels. So basically talking about a patient with hypovolemia or hypotension. So he needs more fluids and more fluids going in there. So this is going to be regulated by the A. So yes, if he needs more fluid, as a result, he's going to be needing more calcium that's going to be reabsorbed so that he can have compression of the vessels because he's in hypotension state. Okay, so it's not fluids. I got confused for a second. I'm sorry. So he's in ACV reduction. So he has low volume. He's in hypotension state. He's going to need more calcium so that he can compress the vessels and regulate the blood pressure. And there is alkalosis. Honestly, guys, I'm not sure about the mechanism of alkalosis. I did try to look it up. I couldn't find anything. But I guess for the exam, a way for you guys to remember it, that alkalosis causes increased reabsorption. I'm not saying that it is the correct way that is behind this mechanism, but yeah, you could use it just to remember, is that the alkalosis is basically too much base, and the base is HCO3 minus. But all I'm focusing on is the negative charge. So since it's a negative charge, it's going to be absorbing the positive charge, which is the calcium. So calcium is positive, so it's going to absorb the calcium. So that's why there's increased reabsorption in alkalosis state. Tamam? Calcium reabsorption. This is again the same slide. I just added here so you guys can see that in one of the slides that we talked about calcium reabsorption, there was PTH here. And this is how the mechanism of PTH. Tamam? All right, this is all for the lecture. Do you guys have any questions? Is it all clear? Do you want me to go back through any slides? Okay. Let's go through the questions. Inshallah, they're going to be easy. Inshallah, the lecture, everything is going to be easy. So, okay, the first question is, in a dehydrated person, okay, this is your clue, dehydrated person, with normal kidneys and high ADH levels, which part of the nephron normally reabsorbs the smallest amount of water? See, I said that this is your clue, but the thing is with a lot of the questions that you get is the entire scenario, and then the last question is something completely unrelated. But yeah, so you said B. Okay, I got a B, but try again. It's not B. Oh yeah, it's not B. Oh wait, yeah, it's not B. Okay, I got confused. C, D, and E are for the NaCl, so no water. Yeah, exactly. Okay, you misread the question. See, you got the idea, but you misread the question. It asks for the smallest amount of water. D and E are the late distal tubule and the collecting duct. The late distal tubule and the collecting duct. I mean, wait. So yeah, so these areas here, like we talk about the late distal tubule and the collecting duct, these guys have some water reabsorption. But C is the thick ascending limb. So it's an ascending limb. Ascending limb, we said, is only for sodium chloride. That's why it's C. Wait, let me go back to the part here. Okay. So here, we're talking about thick ascending limb. It only reabsorbs the salt. There's no water going to be reabsorbed. So that's why the correct answer here was C. But I think you got the idea. You probably got confused with the graph. I apologize if the graph was confusing. But did you get the idea of like why is it C? Yeah, the smallest amount. So if there is the smallest amount, that's why we went for. Okay, I get your point. You mean that there is a small amount that is reabsorbed, but it's not. Okay, I see. So you mean that there is a small amount that is reabsorbed, but C is actually there's no water that's reabsorbed. Okay, I guess this could be confusing then. With I think that when they put the question, their point was having it be C because C there's no reabsorption of water. But you're right. Plus, wait. So you said C, D, and E are for NaCl. I'm not sure, but يعني, I could look into it later. But it's not really something that I want to look into because you got the idea right. But I guess it's the way that the question was worded. Okay, I'm sorry. The question was worded might be confusing. But yeah. Oh, so you got that. Okay. I'm sorry. Okay, so the next question, acute metabolic alkalosis, the effect on potassium secretion by the cortical collecting tubules. Let me find the pen. Okay. So the effect of alkalosis on potassium. B. Yep, you're right. Because A plus and potassium are going to be exchanged with each other. I'm just leave it here if you want to look at it again. H plus and potassium will exchange with each other. Last question. If a person maintains a high concentration of food or potassium, so high potassium diet, which part of the nephron would be expected to reabsorb the most potassium? Choose the appropriate nephron site in the figure below. So which one reabsorbs the most potassium? You said D. The correct answer here is, okay, this was a tricky question. Okay, try again. It's not D, try again. D or E. It's also not E. It's a tricky question. If I don't know, think about it slightly, try to get the basics, and you'll get it if you think of the basics, like the general concept that we talked about at the start, the general concept. Where would we want to have the most reabsorption? Yes, you're right, at the proximal tubule. So for everything, the most reabsorption is done at the proximal tubule. See here, it's 80% was at the proximal tubule. But D and E, you're right. That's why I put it, because it could be tricky because they do increase with food. However, most of it is 80%. Most of it is in the proximal tubule. Don't get confused with the 100% here, because like this, when it's red, it means that it's a must, that 80% is reabsorbed here. So whatever is remaining here is going to be reabsorbed in this part. Tamam? So again, it's proximal tubule. But now you got it right. Yeah. You don't have to memorize the person, it's just the concept. Have any question? Was the lecture here, inshallah? No worries. I'm stop the recording. Thank you guys so much for listening. Inshallah, it was beneficial, and good luck in your exam.